second video on the 1-2 notes, but it actually covers part 3 of the notes that have been uploaded into the notes folder in Schoology. So now we're going to start talking about reflection. We've already done translations where we shift our graph up, down, left, and right. Now we're going to be looking at flipping your graph over some type of line, which is called the line of reflection. So we have this example 2, graph the function using the parent function as a guide. And I'm going to scroll down here so we can see a little bit more of the graph. So we have this equation, this g of x is equal to negative x squared. Looking at the equation, you need to figure out what the parent function would be. So this g of x does have a square in it, which means the parent has to belong to the quadratic function family. And if you recall from the table in the very first video, the graph to do the parent function for this is negative 2, 4, negative 1, 1, 0, 0, 1, 1, 2, 4. So that is my parent. Now, to graph this g of x function, the only thing that's changed between the parent equation, which I can write up here, that is the parent. The only thing that's different between those two is the placement of the negative. The negative is out in front of the x squared, so you're not making the x negative, you're actually making the y value that you get back negative, which means all of these points are going to be at the same x position, but they're going to be flipped on the other side of the x-axis. So this point here at negative 2, 4 is going to be down at negative 2, negative 4. The point at negative 1, 1 is going to be at negative 1, negative 1. 0, 0 lies on the x-axis, so it's going to remain 0, 0. 1, 1 is going to move to 1, negative 1, and 2, 4 is going to move down to 2, negative 4. So you can see we have the same shape as we did with the parent graph, but now our graph is flipped upside down. And that's what the negative in front of the function does. It is actually going to reflect over the x-axis. And this is what you'll see in most of these instances. It is possible to reflect over the y-axis, but again with a quadratic, because of the way it's opening, when you reflect over the y, it's basically going to spin around and it's going to look like the same thing, but this does come up in IXL. So if you were going to reflect over the y-axis, you would see something like this, where the negative is inside of the square, or if it was an absolute value, it would be inside of the absolute value. So if you reflect over the x-axis, the negative is on the outside. If you reflect over the y-axis, the negative is on the inside. Okay, now we're going to look at dilations. So we are going to graph this function using the parent function as a guide. So again, we want to look at the equation here. I have these bars, which means I'm dealing with an absolute value. So the absolute value, the ordered pairs that we use to graph those are negative 2, 2, negative 1, 1, 0, 0, 1, 1, and 2, 2. And that'll give us our nice V shape there. So this equation was absolute value of x. You see I've added a 3 on the outside, which means whenever I plug in my x values, the y that I get back is going to be 3 times as large. So if I have the point negative 2, 2, my y value is 2, 3 times that 2 is now 6. So instead of being at the point negative 2, 2, this is going to be at the point negative 2, 6, because it is 3 times the y value. The point negative 1, 1 is now going to be at negative 1, 3, because the y value of 1 times 3 would give me 3. 0 is going to remain the same, because 0 times 3 is still 0. 1, 1, again, my y value is 1. When I multiply that by 3, I get 3. And then the 2, when I multiply that by 3, that's going to move up to 6. So you see the x's are still at the same positions. They are now 3 times as steep. So 3 times all of your y's because that 3 is on the outside. This is actually what we call a vertical stretch because you're pulling on it in the vertical direction to make it much skinnier, much longer than what it was originally. All of this stuff with stretches, we also have things called compressions. Those will be discussed in a few slides. I actually have a really nice summary page to let you figure out whether you're dealing with vertical or horizontal and a stretch or a compression. Okay, example 3b. Now we're going to graph this function, again, using the parent function as a guide. So if you look at the equation, there's a square in it, which means this has to belong to the quadratic family. And again, the quadratic function parent is f of x equals x squared or y equals x squared. I have negative 2, 4, negative 1, 1, 0, 0, 1, 1, and 2, 4. So that's the original. So now you have to look at where the number is. We have a fraction of 1/2 inside with the x's. So that means we're going to be taking half of all the x values to get the same y. So I am going to put a dot at 0, 0 because when you take half of 0 or half, it doesn't change any. So I am going to have that 0, 0. But in order to get this y value at a positive 1, I would need something that's actually going to be double of what I had originally. So instead of being, in order to get the same x value of negative 1, I would have to put a negative 2 in there to get the same thing. The same thing I'd have to get a positive 2 to get that same height. Because you want something, you want a number 1 square, well half of 2 is what's going to give you that 1. And the same thing here, we have this 2, 4. To be at a height of 4, I actually need to take half of some number to get a 2. That's going to put me at 4. So that's going to stretch out to 4, 4, and the same with the negative 2, 4. So you're going to be actually changing the x values that you have in this one in order to reflect the same y values that you had in the original. This one can be a little bit more difficult to comprehend because we are dealing with the horizontal, which is the x, instead of the vertical, which is the y. This is what we call a horizontal stretch. The horizontal stretch, because you're acting upon the x values because that 1/2 is on the inside, and so you're widening out your graph. You're making it take up longer. It's almost, instead of thinking of half of x, it's almost like you're doubling the original x because you had to take half of some new x to get the x that you started with. This is a horizontal stretch. So we didn't actually do a compression example, but that is down here. Compression is where you are squeezing things. Stretch is going to be when you're stretching them. So the stretch is some transformation that's going to increase your distance between your points in the graph by some factor. Example 3a has your vertical stretch by a factor of 2, and 3b is a horizontal stretch, and technically it's also by a factor of 2 because you had to take half of some new x. So you had to double your original x to get your new values. And then you have a compression. Your compression is the transformation that's going to decrease the distance between the points by some factor. Now, how to figure out whether you have a stretch or a compression, whether it's vertical or horizontal, that's going to be on the next page. You do need to be careful because with stretches and compressions, there's always multiple ways to express them, especially if you don't know how the original equation is set up. And I like using the Play-Doh example for this. If you have Play-Doh and you're pulling on it up and down, you know it's going to get really long and skinny. That is the same thing as if you had it and you were pushing in on it from the sides. Because if you're pushing in on the sides, it's also going to stretch up and down. What determines whether it's that compression or that stretch is going to be where your numbers are. And that's what this chart goes over. You scroll a little bit so you can see that. This is something I would suggest that you copy down. It does appear in IXL if you click on either Learn by Example before you do a section, or if you get a question incorrect, there's a chart that goes over this. The key is to figure out where your number is. That's what I've highlighted in yellow, and what your number is. Is it a fraction? Is it a whole number? So on the top here, we have vertical stretches and compressions. On the bottom, we have horizontal. For vertical, your A's are always going to be on the outside. So it's going to be some number times the function. If that number is a whole number, which is the top, that's A is bigger than 1, then it is going to be a vertical stretch. If that number is a fraction, it is going to be a vertical compression. Now I did put this word in here, shrinks, for that. IXL uses the language of shrink instead of compression. So I just want to make sure that we understand what that terminology actually means. So again, outside whole number is going to be a vertical stretch. Outside fraction is going to be a vertical compression or vertical shrink. For horizontal, your number is going to be on the inside with X. This is like example 3B. If that number is a whole number, that is going to be a horizontal compression or a horizontal shrink. And you see there we have that shrink again. If that number is a fraction, so here I know it says where A is greater than 1, but it has 1 over A. So if it is a fraction on the inside, that is going to be a horizontal stretch. So that would be pulling on it horizontally. That is what we had in example 3B. So this was example 3B. This one was example 3A. What was this first option here? So we have one more that we're going to look at, and this is just going through and stating some basic transformations that are necessary. It says, state what's necessary to transform the solid line into the graph of the dotted line. So for part A, our solid line is a quadratic. I am going to compare vertex values. So I'm comparing this dot here to this dot here. Well, to go from this solid blue line dot to the dotted green dot, we are going to the right one and up 2. If you wanted to write the equation for that, that would be y equals, your A would typically go next, but the A value is 1 because I don't change how wide my graph is. So this would be x minus my h, which was 1 because that's my left and right, squared, and then the k on the end, which would be plus 2. So that would be the equation that matches up with A. For part B, this is an absolute value. Again, I'm comparing dot to dot. So to go from the solid blue to the dotted green, we are going left 3, and that puts my dot in the correct position, but notice my graph also got flipped. And because it got flipped over the x-axis, we say that's a reflection. So reflect over x-axis. That is going to mean that your A value is -1. So the equation for this one is y equals negative, you could put a -1 there or just a negative sign, absolute value of x minus h. Well, h was a -3 because it went left, so that's going to be a +3. So that would be your equation there for example 4B. I will be adding a video for how to do the specific IXLs, but really everything has been covered within this video and in the previous video. Please go back and look over anything that you're not sure of. Again, go back to this previous slide that had the horizontal and vertical, the compressions and stretches. Please copy that down so you have it somewhere to reference while you're working through these questions. And as always with everything that we do, please contact me if you need anything else explained or if you have any additional questions.